So we're now going to look briefly at the intersection of lines and curves. If two lines or curve, I'm going to call them lines in general from now on, whether they be curved or straight or whatever, but if two lines are going to meet, that the points where they meet, they share an x and a y coordinate. Now, you've mainly dealt with straight lines before now, so the options with straight lines are quite simple. Either they're parallel and they never ever meet, or they do cross at some point, or in fact, they might be completely coincident, they might overlap and have infinitely many solutions. If you've got, for instance, a quadratic in a straight line, you might have the straight line so that it doesn't meet, in which case there will be no intersections at all. You might have it so that it just, that's a bad example, it just touches at one point, or you might have it so that it cuts at two different points. So if you've got quite complicated equations you're dealing with, you're not really sure how many times they're going to meet. But if they meet, they share an x and a y coordinate at that point. So let's look at this first example. You're given a line here, and a line here, both of these are straight lines, and you're asked to find out where they meet. Okay, so to find out where they meet, we're going to solve them simultaneously. We're going to say, right, well, there's an x and a y coordinate they have in common. What is the x and a y that works in both equations? So I write them down in the standard format for simultaneous equations, which is with the x and y's on one side and the number on the other. I go through the solving process and I end up getting that x is 2 and y is minus a half. This is the x and the y value that works in both of these, and that's the point of intersection. Of all the infinity of possible x and y's that work in this, and of all the infinity of x's and y's that work in this, the one that works in both is this one here. There are other ways of doing it. To solve things simultaneously, you can do it by substitution, for instance. So you could, being a bit over the top about it, you could get y completely by itself. You could say that y is 5 minus 3x all over 2. You get y by itself over here, which will give you 7 minus 5x over 6, and set those two expressions equal. That's saying, well, the y's must be the same when they intersect. You could even notice that if this is 2y, then 6y would be 3 times this, and replace this 6y here. Of all the methods for solving things simultaneously, you can pick any one of them. Let's look at another example. So down here, you're being asked when, you're asked to show that this curve and this line do not meet. Now that's possible because this curve here is going to be a quadratic, and this just means that that straight line is positioned and orientated such that it's not going to meet. So maybe something like that, or maybe something like that. So, showing that things don't meet is slightly counterintuitive. If you're going to show that something doesn't meet, you start with the assumption that they do meet. You start working through the question, trying to find out when they meet, and you should obviously get no answers at all. If you try and find out when they meet, and they don't meet, there shouldn't be an answer. So let's start this question. So if I was going to try and find out when this line and this line meet, I would solve them simultaneously. So the first thing I'd do is I would rearrange this to write out that y is x plus 3. Oh, sorry, and actually y would be x minus 3. So at this point here, you could say, well, this expression for y and this expression for y are equal, and then you'd bring this across the other side to get this equation. Or you could even do this by substitution, which is what I've done. I've substituted this way of writing y into this thing here. So instead of writing that y there, I've written out this version of y minus x plus 3. Either way round, you end up at this equation here. The solutions of this equation are when they agree, are when they meet. Now apparently they don't meet, so we're hoping that this doesn't have any answers. So if you want to investigate a quadratic and show it's got no answers, the determinant is the best way of doing that. So if I calculate the determinant of this, I end up getting minus 27. We know from earlier in the course that a negative determinant means that there are no solutions, and so these lines never meet. If they were going to meet, you would go about this method here and you would get answers. I've done the correct method, but got an equation with no solutions, so they do not meet. Okay, so this question features a little bit of the previous idea, but really goes through all the possible options of what you could be asked. And in an exam, you'd probably only be asked to do part 1, 2, or 3. So here, we're given a curve and a line, and we're asked to find what m would need to be for the straight line to just touch once, to be a tangent, for the straight line to cut at 2 separate positions, or for the straight line to never meet the line, for it to have no intersections at all. So let's solve and let's try and find out where they meet. So I'm going to plug this expression for y into this one here. So by substituting this into this, I get this equation here. I'm going to expand this out and collect it together so I've got a quadratic in x. This equation here finds the x values where they intersect. The presence of the m just makes it a bit more difficult. So if I'm asked to find out how many solutions this has, okay, so this is going to tell me where the intersections are, and I'm interested, for instance, in there being no intersections, or 2 intersections, or 1 intersection, then that suggests straight away that I must be interested in the determinant. So let's calculate the determinant of this quadratic. So b squared minus 4 times a times c. This is an expression for the determinant of this equation. I'm not going to expand this. You're going to see that it's much nicer to leave it in this format here. So this is the determinant of the equation which gives the intersections. So I'm going to use this to investigate how many answers this has, how many intersections there will be. So part 1 says that the straight line is a tangent. So there will be one answer to this, one intersection. We know that one answer means that the determinant is equal to 0. For part 2, there would be two answers. We know that two answers means that the determinant is bigger than 0. And if it doesn't touch at all, that means that this has no solutions at all, meaning the determinant is less than 0. Part 1 could be done quite easily, but I'm going to try and do all three parts together, so I'm really going to focus on the fact that this is a quadratic inequality more than anything else. So to solve a quadratic inequality, I'm going to sketch the thing I'm interested in. All three of these are saying something about m minus 7 squared minus 28. So let's sketch what that piece of maths looks like, and then let's investigate when it lies on the x-axis, above the x-axis, and below the x-axis. So if I'm going to sketch this thing here, first of all, it's a quadratic in m with a positive m squared, so it's going to be u-shaped. So to find the roots, if you'd expanded this, you'd have to use the quadratic formula. But in this format here, it's much easier to find the roots. If you set this equal to 0, only for the purposes of finding the roots, nothing to do with this up here, if you're going to find the roots here, then you bring the 28 across, take the square root of it, plus and minus answers bring the 7 across. That's really in the completing the square format. So finding the roots by whatever method, you get the roots are 7 plus 2 root 7 and 7 minus 2 root 7. And so I've drawn a sketch of this determinant. I've drawn a sketch of this piece of maths which is so important to us. So for part 1, I said that this piece of maths had to be equal to 0. It had to be on the x-axis. So that would happen just for the two roots, at 7 plus 2 root 7 and 7 minus 2 root 7. Getting on to the more interesting quadratic inequalities, I'm going to have case 2 when m minus 7 squared minus 28, when this determinant is bigger than 0. So looking at my graph, that happens for these parts of the graph. That's when my sketch of this thing here is above the axis. So I am above the axis for this part, for these ranges of m values rather. So when m is less than 7 minus 2 root 7, here I have a positive value for the determinant, and when m is in this region of the graph, when you plug those values in, you get a positive value as well. Looking at the last bit, when I want the determinant, which I've got a graph of here, to be below the axis, when I want it to be negative, well, it takes a negative value here. It takes a negative value for this range of m values. So I have case 3, when m is between 7 minus 2 root 7 and 7 plus 2 root 7. Those are the three cases there, and it all depends on the determinant. My next example, excuse me, asked me to show that the line y equals mx plus 2 cuts this curve twice for all values of m. What I'm saying is, if you draw this quadratic here, then if you draw me a line with a y-intercept of 2, it doesn't matter what you set the gradient as, it will always cut twice. So, a bit like earlier where we were showing something didn't happen, proving something always happens sounds a bit odd to begin with, so just start every question the same way. Just set off as if you're trying to find exact certain points. So let's find out when these two lines meet. So we set them equal, we really sort of plug them into each other. So this y expression here, I'm going to replace over here. So I've got this thing here. This is the equation which tells me when they meet. This gives me the intersections. So rearranging that and grouping things together, I'm solving this equation. This is the equation, this is the quadratic that gives me answers. Okay, now, apparently, I always get two answers. So if I'm interested in the answers to an equation, particularly one with other letters going on in it, I'm going to investigate the determinant. So the determinant of this will be b squared, number in front of x is b squared minus 4ac. So the determinant of the equation that gives me intersections is this thing here. So let's think about this. If I can somehow show that this is positive, then I will always get two answers for this. I don't know what those answers are, but I will always get two answers. So there must be something about this which proves it's always positive. Well, let's look at this for a second. Now, the way I'm going to do it here is I'm going to complete the square. So I'm going to take the determinant and I'm going to complete the square. And I've got this expression here. Now, looking at this thing here, this is always positive. And the reason it's always positive is, well, first of all, 12 is always positive, and I'm really adding on something else. Now, whatever you do inside this bracket, be it positive or negative, when you square it, it becomes positive. This is a positive thing plus a positive thing for all values of m, which will always be bigger than 0. that thinking's a bit similar to when you did maximums and minimums after you'd completed the square earlier on. So if I go about trying to solve this, trying to find out when they meet, I get an equation which, because of the determinant, is guaranteed to always get two answers. Okay? The alternative way of doing this last bit, if it wouldn't have occurred to you complete the square, is just to draw this. If you sketch this quadratic here, if you sketch the determinant, you'll find that it doesn't matter what m is, you always get positive values. So if you draw it, you get something like that, something which is always above the axis. Okay, so if I was to ask, when does it have two answers? When is this determinant bigger than 0? Well, it happens for any value of m that you choose to plug in. Actually, just when I think about it, if we go back to the original question, let's just draw a little sketch of the original question. So the original question was, if you draw the graph of 3x squared plus 4x plus 1, whatever it might look like, let's maybe draw something like that. I mean, I don't know whether it cuts the axis or not, it doesn't really matter though. If I then draw this graph here, well, I don't know very much about that, but I know that it's got a y-intercept of 2, okay, above the y-intercept of this curve. So it doesn't really matter how you try to draw that. If you try and draw it like that, like that, like that, any straight line you draw through 2 is going to cross that quadratic twice. So the sketch here backs out all of the algebra that we've done there. Okay, so the final example here. So it says calculate the coordinates of the points of intersection of this line and this line. So again, you're going to solve it by simultaneously. Now, when you get a kind of difficult and an easy equation, as I sort of call them, the only way of solving simultaneously is by substitution. If you go back to the very first example here, we did it by elimination, sorry. We could have done it by substitution. We spoke about both ways of doing that. When you've got something as complicated as this, it's going to have to be by substitution. So I want this to be an equation about one letter only. So, for instance, over here, I notice that y equals x minus 3. That's just rearranging the first one, and I use that to replace all the y's in this. If I do that, I'm going to go through this thing here, and every time I come across a y, I'm going to write x minus 3 instead. So x squared minus 3x. Instead of y, I write down x minus 3, making sure I've got brackets there, because this was 3x times y, and y is now x minus 3, the whole thing is there, plus y squared, which would be x minus 3 squared, plus 19. This equation here is going to let me find the x values that work in both equations. Expanding, collecting, timesing through by minus 1 or bringing this across, whichever way you want to look at it, you get to this quadratic here. I'm hoping it solves by factorization, which it does, so I find these two x values here. These are x values that work in both of these equations. Now, I'm asked to find the coordinates, so I need to find the corresponding y values. Now, you've got a choice there. If you know x and you want to find out y, well, it works in either one of these. I would far rather use this to work out what y is than to use this. If you plugged your x value back into this, you'll get a really awkward quadratic, and you could follow that through, but it creates a lot more difficulties than you really need at this point. So, if I've got x is minus 4, I'm plugging back into this to get what y is, and when I've got x is 7, I'm plugging back in to get what y is. This gives me a pair of coordinates here. You really, technically at this point, should check these do actually both work. If you'd follow that other method, you do get a few other solutions that don't completely work. So if I plug this pair into here, it works. If I plug it into there, it works. If I plug this into here and into here, it works as well. That's the end of this section, and that's the end of C1.